Hey, welcome back to the lecture. In this tutorial, center-taped full-wave rectifier is explained. Before going to the working of a center-taped full-wave rectifier, let's first take a look at the center-tape transformer, because the center-tape transformer plays a key role in the center-taped full-wave rectifier. When an additional wire is connected across the exact middle of the secondary winding of a transformer, it is known as a center-taped transformer. The wire is adjusted in such a way that it falls in the exact middle point of the secondary winding. So the wire is exactly at 0 volts of the AC signal. This wire is known as the center tap. The center tapped transformer works almost similar to a normal transformer. Like a normal transformer, the center tapped transformer also increases or reduces the AC voltage. However, a center tapped transformer has another important feature. That is, the secondary winding of the center tapped transformer divides the input AC current or AC signal into two parts. The upper part of the secondary winding produces a positive voltage, and the lower part of the secondary winding produces a negative voltage. When we combine these two voltages at output load, we get a complete AC signal. So the total voltage is equal to V1 plus V2. The voltages V1 and V2 are equal in magnitude but opposite in direction. That is, the voltages V1 and V2 produced by the upper part and lower part of the secondary winding are 180 degrees out of phase with each other. However, by using a full-wave rectifier with center-taped transformer, we can produce the voltages that are in phase with each other. In simple words, by using a full-wave rectifier with center-taped transformer, we can produce a current that flows only in single direction. Now let's see what is a center-taped full-wave rectifier. A center-taped full-wave rectifier is a type of rectifier which uses a center-taped transformer and two diodes to convert the complete AC signal into DC signal. The center-taped full-wave rectifier is made up of an AC source, a center-taped transformer, two diodes, and a load resistor. The AC source is connected to the primary winding of the center-taped transformer. A center tap connected at the exact middle of the secondary winding divides the input voltage into two parts, right? The upper part of the secondary winding is connected to the diode D1, and the lower part of the secondary winding is connected to the diode D2. Both diode D1 and diode D2 are connected to a common load, RL, with the help of a center tap transformer. The center tap is generally considered as the ground point or the zero voltage reference point. Now let's see how exactly this circuit works. The center-taped full-wave rectifier uses a center-tapped transformer to convert the input AC voltage into output DC voltage, right? So I hope you understood that when input AC voltage is applied, the secondary winding of the center-tapped transformer divides this input AC voltage into two parts, positive and negative. So during the positive half cycle of the input AC signal, terminal A become positive, terminal B become negative, and center tap is grounded. So grounded means it is at 0 volts. The positive terminal A is connected to the P side of the diode D1, and the negative terminal B is connected to the N side of the diode D1. So the diode D1 is forward biased during the positive half cycle and allows electric current through it. On the other hand, the negative terminal B is connected to the P side of the diode D1, and the positive terminal A is connected to the N side of the diode D2. So the diode D2 is reverse biased during the positive half cycle and does not allow electric current through it. The diode D1 supplies DC current to the load RL, and the DC current produced at the load RL will return to the secondary winding through the center tap. During the positive half cycle, current flows only in the upper part of the circuit, while the lower part of the circuit carry no current to the load because the diode D2 is reverse biased. Therefore, during the positive half cycle of the input AC signal, only diode D1 allows electric current while diode D2 does not allow electric current. During the negative half cycle of the input AC signal, terminal A become negative, terminal B become positive, and center tap is grounded. The negative terminal A is connected to the P side of the diode D1, and the positive terminal B is connected to the N side of the diode D1. So the diode D1 is reverse biased during the negative half cycle and does not allow electric current through it. On the other hand, the positive terminal B is connected to the P side of the diode D2, and the negative terminal A is connected to the N side of the diode D2. So the diode D2 is forward biased during the negative half cycle and allows current through it. The diode D2 supplies DC current to the load RL. The DC current produced at the load RL will return to the secondary winding through a center tap. During the negative half cycle, current flows only in the lower part of the circuit, while the upper part of the circuit carry no current to the load because the diode D1 is reverse biased, right? Therefore, during the negative half cycle of the input AC signal, only diode D2 allows electric current while diode D1 does not allow electric current. So therefore, the diode D1 allows electric current during the positive half cycle, and diode D2 allows electric current during the negative half cycle of the input AC signal. As a result, both half cycles of the input AC signal are allowed. So the output DC voltage is almost equal to the input AC voltage. A small voltage is wasted though at the diode D1 and diode D2 to make them conduct, right? However, this voltage is very small as compared to the voltage appeared at the output, so this voltage is neglected this time. The diodes D1 and D2 are commonly connected to the load RL, so the load current is the sum of individual diode currents. And we know that a diode allows electric current in only one direction, right? From this diagram, we can see that both the diodes D1 and D2 are allowing current in the same direction. We know that the current that flows in only single direction is called a direct current. So the resultant current at the output, which is on the load, is a direct current DC. However, this direct current which appeared at the output is not a pure direct current, but a pulsating direct current. The value of the pulsating direct current changes with respect to time, and this is due to the ripples in the output signal. So, as you already know, these ripples can be reduced by using filters such as capacitor. And you also know that the average output DC voltage across the load resistor is double that of a single half-wave rectifier circuit. The output waveforms of the full-wave rectifier is shown here. The first waveform represents an input AC signal, the second waveform and third waveform represents the DC signals or DC current produced by diode D1 and diode D2. The last waveform represents the total output DC current produced by diodes D1 and D2. From these waveforms, we can conclude that the output current produced at the load resistor is not a pure DC, but a pulsating DC. So I hope you got the idea. The main advantage of using this center-tapped full-wave rectifier is that you can reduce the number of diodes from 4 to just using 2 diodes. This circuit might be confusing for some beginners, and you might ask, why would I connect my load resistance in such a way? So where do I put my filter capacitor or other components? But this circuit was used only for you to understand how a center-tapped full-wave rectifier is working. A real-world center-tapped full-wave rectifier will look something like this. As I mentioned before, the center tap is adjusted in such a way that it falls in the exact middle point of the secondary winding, so the wire is exactly at 0 volts of the AC signal. And that's the reason why you see here that the center tap is grounded. If we get rid of this filter capacitor for a bit, and if we connect the ground of the load with the ground from the center tap, we will see that this circuit here is exactly the same as this circuit. Before ending the course, I want to show you another circuit so you will understand why using a center-tapped full-wave rectifier is so powerful. A popular variation of the center-tapped full-wave circuit is shown here. This circuit gives you split supplies, so equal plus and minus voltages, which many circuits need. You will see this type of circuit many times in audio amplifiers because they almost always need a positive and negative voltage. But you don't have to worry about that for the moment because we are going to learn about signal amplifiers in the later courses.